All right, here's another example of a function with a singularity. We're going to have a function from R3 to R2, and notice that's the big to small case, going from a big space into a small space, and we'll keep talking about what that entails. Explicitly, it's the function f of x, y, z is z minus x squared plus y squared, comma z. And I made this especially simple to make it work out nicely in the picture, but it really is a very general phenomenon we're talking about. And how do we want to look at this? Do we want to judge things to be good or bad, or points to be good or bad? Well, we saw already in big to small examples that the inputs are more interesting to look at usually. And so we're going to look at level sets. So here's an example of a level set. We're going to pick the output 0, 1. That's a point in the plane. And we're going to look at all the inputs such that f of x, y, z is 0, 1. Here's a tidier notation for that if you know about pulling back sets and looking at f inverse of a set. This might confuse you a little bit if you realize that f is not an invertible function. If it does, then just don't worry about this notation. So let's see what that is. Well, if I look at a level set of a function with two different outputs, I'm setting this function. Let's actually have a notation for that. Let's call that f1 and f2. So they're two separate functions put together into one. It's where f1 is equal to 0 and f2 is equal to 1. So that's a surface. We'll see what it is in a second. This is a very simple surface. It's just a plane, horizontal plane. So let's see what this surface is. I move everything over. That becomes equals x squared minus y squared. That's a standard quadric surface. It's the hyperbolic paraboloid, or saddle surface, or if you're hungry, it's the Pringle. Okay. And I've got that on the University of Minnesota Quadrics gallery right here. Okay. And so what are we doing? We're taking this, what I want to think about is take this surface, the saddle surface, and I'm cutting it with a horizontal plane with z equals 1. That's exactly going to produce this white hyperbola. And so notice that's a nice curve. Okay, so this intersection is a nice smooth curve. Okay, and one other thing to notice is one reason it is nice is that the plane, they don't put the plane in here, but you can fairly easily imagine the horizontal plane that's creating this white intersection. When it intersects the surface, it really cuts through it. It's what's an intersection is called transverse. They don't, in particular, they're not tangent. But what if I take it down to 0? Ooh, now this surface is horizontal right at the middle of the saddle, and of course so is the horizontal plane. One way to say that more precisely is that the normal vector to the surface, which was slanted, has become horizontal, or has become vertical, and that's parallel to the normal vector for the plane. And that's exactly where we're getting something different. We're getting an x there. So let's look at that level set. That's where we set this number to be 0 instead. Okay, so let's turn that into a 0. That turns into a 0. Okay. And so now, instead of getting a nice hyperbola, what am I getting? I just look at both these equations together. If z equals 0, then it's just x squared minus y squared equals 0. Or x squared equals y squared. We've seen that before. It's x equals plus or minus y. It's the x. It's the asymptotes of the hyperbola we were saying before. And that has a singularity, singular at, 0, 0, 0. Okay. And so let's look at the matrix of derivatives and see if that could have predicted all of this. So we look at, you could call it big DF or F prime or whatever. It's got 2 outputs and 3 inputs. It's all the derivatives of that F1 function up here and the F2 function down here. Well, F2 was z, so its derivatives are 0, 0, 1. F1 was z minus x squared plus y squared, so it's minus 2x plus 2y, 1. Okay, so let's see. This is a 2 by 3 matrix. Could it ever be, if it was a linear transformation, could it ever be 1 to 1? No. Big to small, you don't expect 1 to 1. Could it be onto? Yes, it could be onto. And in fact, most of the time it's going to be. Another way to think about it, almost the definition, very close to the definition of onto, is do the columns span? Well, they definitely could. If I have 1, 1, that vector in the plane, and I have something comma 0 that's going off like this or like this, yeah, those are going to span, okay? If these guys are not 0. Aha! But if they are both 0, it's going to be special. Another way to think about it, let's see. What about the rows? Are the rows linearly independent? That would be the good condition. Well, yeah, I've got 0, 0, 1, and then non-zero, non-zero, comma 1, or anything like here, but beyond 0, 0 would be 2 linearly independent row vectors. Okay. So all these could happen, and they all fail simultaneously when x and y are both equal to 0. Aha! X equals y equals 0, that's that saddle point. That's exactly what we were detecting, that we're seeing there, the cross of the saddle, the singular point, that's exactly where x and y are equal to 0. Okay, so what we're seeing is that it could have been onto, the columns could have spanned, the rows could be linearly independent. For most points, when I look at most of these intersections, most points, it's going to be fine, but this is where it fails. Now, this one is one of the most interesting guys. This is the shortest way to say it. It's not onto is when the singularity happens. But let's look at the rows. The first row of this guy is nothing but the gradient of the f1 function. And remember what f1 was. It was the thing whose level set was the hyperboloid. The hyperbolic paraboloid. And so that's that normal vector pointing like this way, or over here it's pointing this way, the slanty normal vectors that generally are in a different direction from the vertical. The vertical was the normal vector to the level set of f2. That's the gradient of f1 and f2. So the gradient being perpendicular to the level surface says, hey, those level surfaces are going to come in tangent to each other and maybe have a weird intersection exactly when these guys are parallel, in other words, where they're not linearly independent. So the rows being linearly independent actually has a very direct geometrical consequence, whether these surfaces come in and actually kind of cut each other in a transverse way, or whether they come in tangent. It turns out that when they come in tangent, they can do more interesting things geometrically and produce singularities. Okay. So, one more example. Haven't done anything where it's the same dimension. Okay. Let's do 5. So f is going to go from R2 to R2. That doesn't look like a 2, does it? And its f of xy is still continuing on this theme of quadratics, of course. X squared minus y squared comma 2xy. It's a very famous function. It turns out one secret rule it has is if this is actually the complex numbers to the complex numbers, it's exactly the squaring map for complex arithmetic, but let's not worry about that too much. Okay, so this is not big to small or small to big. It's the same dimension. Okay, so this is something where we could actually get 1-to-1 anon to, where we could get something that's invertible. But let's see what happens. Okay, so for the picture, there's one picture of this that I want to show you, which focuses on the output. Oh, it's under the Java here. Okay. Here we go. So here's a picture. Yeah, that's good. Okay. Where I've got, here's the input grid. Oh, you know what? It's got S and T. So let me, yeah, I probably want S and T here. Okay, and we could call X and Y the outputs. S squared, T squared, 2ST. I forgot about that. Okay. So S and T are the inputs, and if I look at where the input grid lines go, these are nice smooth curves, and they intersect definitely transversely, in fact, perpendicular. I would like the same to be true of these guys. Now, of course, they're not going to be straight lines. It's more interesting than that. But I'd like them to intersect transversely and be smooth themselves. And a lot of the time that's true, but let me go to here. If I step these guys through, and if I step them through 0, ooh, something weird happens. It changes qualitatively, and it becomes a curve that goes in, bounces off, and turns around. That's suspicious. That's not how normal curves do. And they also intersect tangent to each other at that 0 at the origin. So clearly the origin is a place that's weird. If I go away from the origin, everything's nice. In fact, these happen to be perpendicular to each other. That comes from the complex analysis part, but let's not worry about that. Okay, so clearly it looks like 0, 0 is a bad point by looking at the image curves of this grid. Now, something this applet doesn't do very well is if I look at the opposite, if I look at the grid, the nice grid in x and y, the standard coordinate grid here, I could look at the inverse of that under f. What are, say, all the points that get sent to this curve, or all the points get sent to this curve? Well, that's exactly just looking at level sets. I could look at, if this is x comma y, I could look at x equals 1 or minus 1 or 0. Oh, well, you know what? X equals 0 is the x we were just looking at in the previous example. So where s squared equals t squared. X equals 1 is a hyperbola. S squared minus t squared equals 1. S squared is minus 1 is another hyperbola. What about these guys? If I set y to be a constant, I let x vary to be anything. Oh, st is equal to a constant. Oh, those are these slanty hyperbolas like this. Oh, I should use different colors for those guys. Sorry. Let's use green. So these are the inverses of the other coordinate curve. So this is where, let's see, that's where y is constant. So that's going to be these guys. Okay, and that's going to look like this. This is great. Wonderful. Oh, but wait a minute. What about y equals 0? Oh, that's the axes. That's where either s or t is 0. Aha. So once again, the origin is looking special. The origin is something where each individual level set, the pullback of these curves over to here, has a weird singularity, and they also intersect weirdly as well. It's a plus and a cross intersecting, not like these points where it's just a nice transverse intersection. Okay, so again, okay, let me put this forward. Again, let's look at the matrix of derivatives, and we're going to see that 0, 0 is going to be weird. df or f prime, whatever you want to call it. Now it's 2 by 2, and I've got 2s minus 2t from the derivatives of f1, our first function, and 2t, 2s. Okay, let's see. When is this going to be invertible? What's going to be its how many linear independent columns, rows, whatever? Well, the determinant is not the world's best thing to do in every linear algebra situation, but here it's a pretty good idea. Let's take the determinant. It's going to be 4s squared plus, because it's minus a minus, t squared. Oh, 4s squared plus t squared. Aha! That's 0 exactly when s and t are both 0. At the origin. Surprise, surprise. So this matrix, you put in any numbers for s and t, it's going to have linearly independent rows, linearly independent columns. Rows that span, columns that span. It's going to be invertible. It's going to have all those good properties as long as it's not just s and t equals 0, the 0 matrix. Okay, so that's a little special. This example is a little special. In general, it could degenerate into something that would only have one linearly independent row instead of two. This one actually, when it degenerates, it just dies. It becomes the 0 matrix. df at 0, 0 is 0, 0, 0, 0. But I wanted a simple example, so that's the price I pay. Okay, so once again, we're seeing that when this matrix is deficient, that's when you get the singularities. Okay, so I'm going to wrap this up in a third video talking about what's in common with all these examples and why we would care, some very practical reasons about why we care about when we have singularities.